Hi students, so today we start Math Question Bank 16. Today I am going to discuss some question about Bayes theorem and statistics. So we are going to basically cover probability and statistics. In statistics I am going to look at some simple problems involving the mean, median, mode and when these particular measures of central tendency are the best and are most appropriate. I am Dr. Ganguly. So let's begin with the first question, and this is what is Bayes theorem? And you probably know that Bayes theorem is very important in probability. It's also very important in data science and machine learning. So let's define the Bayes theorem formally. So it's defined as follows, that P A slash B equals P A P B slash A divided by P B. Now this particular nomenclature, that is P then A the slash B, this basically means that how often A happens given that B takes place. So one way to remember it is that B has to take place and then how frequently A takes place. So there are many situations where a particular event happens and then that event, B in this case, has an impact on the probability of the event which follows. So PAB essentially tries to quantify that particular concept. Now, if we write this as PB slash A, then this means that how often B happens given that A happens. So this particular statement is related to, of course, conditional probability. And then you have this relation. Also remember, PA is how frequently A happens on its own, and PB is how frequently B happens on its own. So these probabilities are linked together by the equation which is known as Bayes theorem. Now at the end of this lecture today I'm going to prove Bayes theorem, but before we do, let us get a handle on why this theorem is important and what are possible applications for this theorem. So let us look at this particular question number 2, and this question has four statements. So the first three statements give us some probabilities and the final statement gives us a question. So the first statement is that the probability of dangerous fires is 2% or 0.02. The second statement is the probability of smoke is 0.15, and the third statement is the probability of dangerous fires causing smoke is 0.95. So these kind of probabilities can often be obtained from empirical evidence from statistical data, and sometimes they can also be obtained by asking different experts out there. So these probabilities have been obtained using some mechanism. Now the question is, what is the probability of a dangerous fire when there is smoke? And this question becomes important because, for example, if you are going to make a call to the police or to the fire brigade or call 911 or very important numbers, then if you see a smoke, should you be calling the particular fire department? So we are going to estimate this probability here. Now let us look at the probabilities which have been given in this problem. So we see that P fire is 0.02. So this is the probability of the fire. P smoke is 0.15. That is the probability of smoke. So these are given in the first two statements of the problem. Now from these two statements, of course, we can get two things in the Bayes theorem. But let us also look at the third statement, which is that the probability of dangerous fires cause smoke, that is 0.95%. So essentially what this means is that the fire happens and then that leads to smoke. That probability is very high, that is 0.95%. So of course you can imagine the situation that in almost all fires which are out there is going to be smoke coming out after the fire has begun. So this can be represented as P smoke slash fire equals 0.95. And now we write down the Bayes theorem here, and then what we do is that for A we put in fire, for B we put in smoke. So then I can rewrite the Bayes statement or Bayes theorem in this form, which is more amenable to the problem today. So we can see here that P fire is there as 0.02, we put it here. P smoke fire is 0.95 and P smoke is 0.15, and together with these three numbers we obtain that P fire smoke is 0.1267, or it's about 13%. So there is about 13% chance that smoke indicates fire. So if we see the presence of smoke, there is a 13% chance that there is a fire going on there. And so I would say this is a good enough reason to call the fire brigade. If you are somebody who is more of a cautious nature, you may want to investigate more before you call them. So you see in these cases that the probabilities can be obtained for very practical type of situations. Now let's look at a more complicated question, but these type of questions are extremely important in various diagnostics problems. And in diagnostic problem, we have certain things such as we have a test which essentially tells us a certain problem is there, but we do not know how much we should believe this test. So in this particular problem, we have several values of data which are provided or probabilities. For example, we have the information that a drug test is there and this is 92% sensitive. That means there is something known as a true positive rate which is 0.92. That's the probability, and therefore this drug test will correctly figure out drug users 92% of the time. So this is one piece of information we have there. The second piece is that the drug test is 85% specific, and this essentially means that the true negative rate is 0.85. That means the drug test will identify 85% of non-use by non-users. So this is a case where if a non-user is tested, there is a 0.85 probability that this person will be identified as a non-user. However, there is a 0.15 probability of false positive. That means this guy is a non-user, but he is flagged as a drug user. This is not a good situation to be in, but this is very typical of many diagnostic systems that you have something known as a true negative rate and you also have something known as a false positive rate. So this particular nomenclature is quite ubiquitous in many diagnostics type of problems. Now there is a certain fact known from the population that the prevalence of drug use in the population is known to be 5%. So the probability would be, of course, p is 0.05. And the question is, what is the probability that a random person who tests positive for drugs is a drug user? Now, a normal person may just think that, okay, this guy has tested positive for drugs, he must be a drug user, let us put this guy in some institution. But let us use Bayes theorem before we jump to that concept. So from the numbers we have been given here, we can see that p user is 0.05. That's from this third bullet point here. We also see that p positive slash user is 0.92. So this is coming from the first bullet here. That means the fact that a particular person, or rather I should say here more formally, that P positive user is the probability of someone being a drug user given that they tested positive. So this particular number is given as 0.92. This is the true positive rate for this drug test. But there is an alternative number which is more interesting to us, that is P user slash positive. This is the probability of someone testing positive given that they are a drug user. So we are going to find that out. Now, of course, to find this P user positive, we will use Bayes theorem here. But from the information we have got previously, we have only some of the information. We have P user is 0.05 and we have P positive user is 0.92, but we do not have P positive here, so we have to find that. Now we are going to use the next two pieces of information to figure out what is P positive. So of course these pieces of information give us the following idea. One is that we have this fact that the drug test is 85% specific, or the true negative rate is 0.85. So that's one number we can probably use. And then the second situation is, of course, that it is 15% false positive, and so the false positive rate is 0.15. So this is the next piece of number. Now what we do is we have to use the law of total probability here to get P positive. So P positive can be written as P positive user into P user plus P positive non-user into positive non-user. And we know that the positive non-user is going to be 0.15. That is from this probability here given in this purple. And we also know that since P user is 0.05, P non-user is going to be 1 minus 0.05, and that is 0.95. So I can put these different numbers in this equation of total probability, and I can then calculate P positive to be 0.92 into 0.05. These are the first two values here. Remember, P positive user is 0.92, P user is 0.05. And the second cases involve P positive non-user, that's 0.15, and P non-user is 0.95. So totally I get this probability of P is 0.1885. Now I simply go and I put this P positive in the Bayes theorem, and I obtain the probability to be P user positive is 0.244, which means that even if there is a positive drug test, there is only 24% probability of this person being a drug user. So we have to be careful about jumping onto decisions just because of some drug test, and we have to be conscious of the fact that many times these tests which are out there, they have these things called true positive, true negative, false positives, and so on. And Bayes theorem provides a way to make better decisions using different probability values. Now let's look at some important concepts related to central measures. And generally we have these measures known as the mean, median, and mode. So I'm going to give you three problems in which three different measures are probably the best measures here. Now, in this case, the question is that what is the best measure of central tendency to quantify this particular data set? So in this case, the data set is that we have income per year for men who are more than age 21 living on a particular street. Let us say this income is given in $1,000. And so you will see that income in this case, there are 15 individuals here, is very spread out. So what often happens with income is that many of the people may have similar income, but some of the people have very high or low income. So in this particular data set, we see some large numbers like 920, 510, 430, but we also see some small numbers. For example, we can see 25 here, which is relatively small. We can also see 45, 47. So in cases like these, what happens is that the particular outliers which are there in data, such as this 920 here or 510, will have a big impact on the mean value here. So the better value would be the median. So to obtain the median of these numbers, what I do is first I created a sorted list. So that means I go from the minimum number, which is 25, to the maximum number, which is 920. And then I simply take the value at the middle here. So once I sort these numbers out, I have to take the middle value here, which in this case of 15 numbers here is going to be the 8th number, and that is $82,000 per year. That would be the median income for adult men on this particular street. So in this particular case, wherever you are dealing with variables such as income, wealth, and so on, it's better to use median values. Now the second case is a similar sample, but this time we have taken the height of these men. And when we take height of people, it's a physical variable, so naturally they are going to be bounded between some reasonable numbers. Very often this distribution is going to follow a Gaussian distribution or a normal distribution. So in this case, you can see here that most of the people are in the range of 5 or 6 feet. So that's the typical height of most people who are out there. So what we can do here is we can actually take the classical mean, and that is simply going to be the sum of all these numbers divided by the total of the numbers, and that comes out to 5.628 feet. So in cases of many variables which are coming from physical sources, such as if you are dealing with height, if you are dealing with weight, and so on, the mean is often a good number to use, and the mean tends to be something which is good for numbers which tend to be normally distributed. Now finally we turn to the third measure of central tendency, which is quite widely studied, at least if not used, and that is mode. And very often people are confused as to why is the mode ever being used. Now the mode is actually not used too much in case where numbers are present, but it can often be used to categorize a certain concept. For example, let us take the case here where we look at the color of the cars driven by the men here. So we again have 15 men here, and we have made a list of the color of the cars. So you can see these are red, blue, white, silver, green, all the way here. So there are 15 different colors here. Now, whenever you have data like this in form of certain categories, what one can do is one can take a look at the different data here. So I have tried to see, for example, there are two red cars, there are two blue cars, there are six white cars, there are two silver cars here, there are one green car, and there are two black cars. And so from this we can figure out clearly that white cars are more prevalent, or white is the mode here. So actually, as far as the mode is concerned, that clearly tells us that white cars are most popular, at least in this neighborhood. And in fact, white cars tend to be highly popular. If you go around your neighborhoods and see the cars most people drive, you will find that white cars are quite a substantial portion of the cars. And of course, one of the reason could be that white cars are somewhat easier to see at night, and therefore they are safer from a driving perspective. At least if you search Google, it does give you some information that white cars are more safe, and black cars tend to be slightly unsafe as far as night driving is concerned. That's because the headlights reflect well on white cars. Now, final question, of course, like I mentioned when I started this lecture today, is how to prove Bayes theorem. Now, Bayes theorem is quite ubiquitous out there. There are a lot of problems where we use it. And of course, as you would understand, it is derived from conditional probability definitions. So if we look at the definition of conditional probability, we know that PA slash P is PA intersection B by PB, and we can write a similar equation by flipping B and A, and that would be PBA equals PB intersection A by PA. Now looking at these two, we can clearly realize that P a intersection B should be equal to P B intersection A, because this is the probability of the event if A and B both take place. So again, that is the intersection, and if you think of a Venn diagram, these are going to be same. Now using this fact, I can write two values here, or two different sides of an equation here. So I can write P AB into PB, that is this equation, is equal to PA into PB slash A. And from this equation, I can immediately rewrite to get PAB in this form here, which is the Bayes theorem or the Bayes formula, which is very important in data science, probability, and even machine learning. So this was a brief lecture today which introduced you to the Bayes theorem. In my previous lecture number 15, I introduced you to basic concepts of probability. So now you have some basic ideas about probability and how you can ask questions on this particular field to test out students and if they appreciate the basic knowledges of probability. And in the next lecture, I think I'm going to look at some different aspects, certainly conic sections, and also how conic sections tend to be related to partial differential equations and can be used to classify partial differential equations of different type. So I will see you in my next video, and I will see you then.